Good afternoon, this is Schweitzer, and I'm going to start walking through some of our answers to, this is a honors chemistry review. Test is coming up here fairly quickly. So let's walk through some of these. This is the amount of energy you need to remove an electron that we call ionization. Above is a model of dot diagram structure. All the following can be inferred from the diagram except, okay, so it's got 6 valence electrons. That's what I would get out of this thing. So group 16 is correct. Has 2 half-filled p orbitals. On this case, like for example, if we have oxygen, it would be one of that family, and it would be 2p6, which would look like that, and would be 2p4. So that would be there we go, match it up, and using Hund's rules, that would also is true. Has at least 10 internal electrons, and depending on the actual size of the atom, Bohr diagram wise, we don't really know how many internal electrons we have. This only shows outer ones. That one I'm questioning. Can form a charge of -2. Yes, that's similar to oxygen. Has at least 4. X has at least 4 p orbital electrons. Yes, at least 4. Yes. It could have more internal ones, but C looks like the one that's incorrect. So that is the one we want to take. Which of the following sets of quantum numbers describes the valence electron? So we introduce these orbitals, and it's giving a number for this thing. So energy level is 1. The orbital type, so it's giving a number here, and then it's showing that S is 0 for suborbital, and it's got some. We talked about this in class, how we number the suborbital, and a +1/2 for the spin. So we're looking at ground state for gallium. Now gallium, if you find it on the periodic table, ends in 4p1. Okay, so this is the 4th energy level. It's a p orbital, which is technically a 1. Now a p orbital can have any of these options. So any of those could be the next number, and then it can either be +1/2 or -1/2. Which of these options here fits? So 4-0 out, 4-0 out, 4-1-1. This looks like an option. It's got a 1, and a 1's an option. In this case, 2 is not an option. It's got to be 1-0-1. So that one's out, and then there you go. C is the option here. This is the electron configuration that your orbitals that are in quantum numbers that are describing it. Okay. O-2, F-1, and neon all have the same number of electrons, which atom is bigger and why? Alright, well, oxygen is bigger because it has the least number of electrons. Therefore, it would be A. An impossible electron configuration, so we're looking for something that just doesn't work. There is no such thing as a 2d10. We can take electrons, like in this picture here, and shove them up into higher energy levels, into existing ones, but there is no 2d. Regarding the S versus S-2, S is smaller than S2 due to more electrons. S doesn't have more electrons. S is larger than due to more protons. They have the same number of protons because there's both sulfur. S is smaller due to larger first ionization energy. It doesn't sound like it says a whole lot of anything versus what we're talking about. S-2 is bigger due to more electrons repelling each other. That is what we would describe it in class. Ground state configuration for negative ion of a halogen. So all the halogens on the periodic table, and you'd make sure you want to, if you aren't familiar with all those, there's a video on this basic information of the periodic table. It's talking about all of these halogens. This is on the non-metal side of the periodic table. Here's my stair step. These are the halogens. They all have 7 valence electrons, and they all form -1 charges. They all end at normally end at the p5, meaning that'd be 2p5, 3p5, 4p5 on their configuration. When I give them an electron, they'd end in P6. So they'd be just like a noble gas, which is a P6. So we're looking for a P6. There's a 5 there. Here's a P6. Here's a P6, but it's got this weird, again, thing in there. 5 and 5. No, 5. This is the one right there. You can actually tell this is the 3p6. This would be the configuration for argon, or same thing for Cl negative, which is what they're talking about, the negative ion of the halogen metal. Important to try some of these on your own. Alright, so we got this thing here, and what we want to describe this, D is the ground state, B is the excited state. This is where energy input. And I'm going to give myself some room here. Erase some of these things. Okay, so we're putting energy in to excite it. So energy input. And then this is where it falls down. Energy out, which is in the form of a photon. So which one is this? Okay, so A, we want this A to be out. Energy light produced. Okay. Only one that's got light produced. I would think D has to be the answer. B, let's just confirm with B. B is going to be right here. Excited state. There it is. Energy added and ground state. So D is the answer. A little confusing how we have the letters up top there, and that was pointed out to me, and have to do something different with how I label those options. All right. All right. Ground state configuration of a common ion. Common ions are optimal ions of an alkaline earth element. On the periodic table, the alkaline earth metals is this second column right here. We do know these form positive 2s. Now, once again, the reason why they form positive 2s is so they can rotate back to have the same configuration as noble gas. This is an important concept. Again, that ends in a P6. Just like the halogens are trying to get to a P6, so is everybody else. They're all losing to get back to a P6. So which of these has a P6? Again, the only one with P6 is this guy. There's an odd one here, and those are all different ones. So this here is the configuration for argon, and I also mentioned it could be a configuration for Cl negative, but it could also be Mg plus 2, which is that chemical right here as it rotates back. All of them getting to be the same configuration as argon. Based on the data table above, which of the following correctly predicts the relative strength of attraction of zinc, calcium, and barium ions to water molecules in a solution from strongest to weakest? Again, we're looking at just the size of the atom. This is a Coulomb's law problem. Force equals the charge of apparently the positive item, which is this guy, and water has a negative on it, and then the distance between them. Okay, so we want to go with the biggest attraction is the smallest one. So zinc is on top, and then barium's on the bottom. Zinc on top, barium on the bottom. So these two are out. And so A says, because the smaller ions have strong Coulomb attractions to water, and because the smaller ions have are more electronegative. We really haven't talked about that, so it's just a nonsense. And A is pretty good, pretty well written. All right, moving on here to a little bit of a matching. All right, in this case here, we have, all right, number 11, a blank is two atoms that have the same number of protons, different number of neutrons. We're talking about a isotope. First family of the periodic table is called the alkaline metals. The blank quantum number represents the energy levels. That would be the principal. Two electrons in the same suborbital have different spin. A blank is a subatomic particle with a positive charge. It's a proton. The blank family elements are very unreactive, noble gases, often also referred to as inert. The blank is a sum of protons and neutrons. They both have mass. That would be the mass number. An atom that has gained an electron in order to fulfill its outer shell. Okay. Gaining an electron is an anion. A gas solution is an indicator of a chemical change. That's an old question. Review. Positively charged particle is called a... Now again, you could put down proton, but of the options listed there, maybe this is the time to use the cation. Alright, rate the electron configuration for arsenic. Arsenic should end in 4p3. So I'll do that quickly here. AS 1s2 2s2 2p6 3s2 3p6 4s2 3d10 4p3. Write the shorting configuration for barium. Alright, you find barium. It's in the alkaline earth metals. The previous noble gas to barium is looking like xenon. Bracket that in xenon. And then just start out as being 1, 2, 3, 4, 5, 6 throw down. 6 S 2. Alright. We got write a longhand orbital notation for oxygen. Okay. Oxygen is 1s2 2s2 2p4, including the orbitals here. Following Hund's rule. Number 83, number of protons. 83 is going to be bismuth. 83 is number of protons. Mass number is adding these two together, so 3, 8 plus there's BL1, so that's just 213. Number of electrons, the charge is none, so it is 83. I'm not going to do the next one because I'm running short of time here, but this is the mass number, and then this is the number of protons, and this is the charge. The alternate way of putting that. In lab, we burned metals to get lots of light. Okay, how does this work? Make sure you show your picture. Electron ground, electron excited, comes up. As you put in energy, as it falls back down, it gives off a photon of light. The most abundant isotopes of oxygen. Okay, so this is a unique question here. We have H2O, and if we could have the lightest version, would be have version 1, 1, and 16 is the lightest version, and then the heaviest version would be, and this thing weighs a grand total of 18. 16 plus 2 is 18, and then the heaviest version is going to be a 17 oxygen, a 2 for the hydrogen. So these are the masses of these guys: 17, 18, 19, 20, 21. And I'm sure I can make a version of every one between. So 18, 19, 20, and 21. So 4 options. There's 4 different weights for water. This is something. The next one is talking about 2 different atoms removing electrons. As I look here, this has got more electrons being removed, and this one here increasing energy this way, so this atom is harder to remove from. Both of the peaks represent electrons moved from the same energy level but different atoms. Which of the following assumptions is true or false? Element A has more electrons removed. This is A right here, and this is B. That is yes, because of the larger spike. B has a larger nucleus. Yes, because it's harder to remove it. A has a larger first ionization energy than B. Well, in this case, the fact that it has larger first energy, first one, I'm going to say false on this guy. Maybe we don't have enough information about this atom, but in this case, because we don't have any information about the radius, we're only taking away some of these electrons. I don't know if there's enough information here to even answer that question. We're only moving a couple electrons. There could be more of them. We don't know how big it is, per se. It could be, well, you could even say the fact that since B has more protons, that eventually it would be bigger, a larger atom, and then therefore maybe that electron, the first one, would be easier to remove because it's bigger. So if I go with that analysis, then the A has the largest first ionization energy. I would say that would be false, again, because it has a smaller radius. Below here you'll find all of your stuff for calculating out your objectives. Please do so, and how you did. Thank you.